In this video, we are going to take our basic definition of a group and we are going to push it a little bit farther to start seeing how we use those properties to draw more conclusions about the structure of groups. To begin, I'd like us to review that definition of a group, which is a big, long definition, and I want us to just focus on this property that I numbered 2, which is the identity property. It's highlighted up here. There exists an element of G that we denoted by E, such that no matter what other element we might have in the group, A dot E is equal to E dot A is equal to A. Recall that one of the things we noted when we studied the definition of a group originally is that the group operation need not be a commutative operation, and so requiring that A dot E be equal to E dot A, in addition to the fact that we require it to be equal to A, we're requiring something even stronger. Not only does this element need to exist, but it must commute with every element of the group. But what I want to draw your attention to is the fact that we stated that there must exist an element of G with this property, and existential quantifiers are very forgiving. We're saying that one thing needs to exist, and then we've called that element the identity of G. Typically, the word the is reserved for unique things. It is the identity, the one and only identity of the group. However, we have not required that this element that must exist be unique. To complicate things further, when we studied numerous examples of groups, we always found some identity, and in all the examples we can think of, the identity of the group is unique. So when we really pay attention to what this property is saying, it makes us think of some questions. We are only requiring that there is at least one identity element of the group. In the many examples we've studied so far, there has only been one identity, and yet that's not required. So that begs the question, are there other examples of groups that have multiple identity elements? In which case, we really ought to study those groups because they would be new and interesting and have a different behavior than the groups that we've found. Or is it a consequence of this definition that the identity of the group must be unique? And if so, how would we prove such a thing? So this is part of what I mean when I say this is a big, bad, long definition. Not only is it literally long, taking up 4 requirements that are quite complicated, but every little word is packed in here just so, and we will need to use every little word to do proofs in abstract algebra. Now, as it turns out, the identity of a group is unique. We're not lacking in examples. No matter how many groups we look at, we will never find one with more than one identity element. We don't need to require in the definition that the identity element of a group be unique because we can prove that the identity element of a group must be unique just from its very existence, which is sort of interesting. So what I would like to do is walk you through a proof that an element is unique because that's a very common theme in mathematics. How do we prove that there's only one of something? That something is unique. That's a property that mathematicians like a lot when something is unique and provably so. The standard method of proof here is to assume that you have 2 of these things. Now we're not assuming that we have 2 different of these things. We're just assuming we have 2 variables, each of which represents the thing. That's the way that these proofs always start, and these proofs always stop when you have a statement of equality, which is that these 2 things that might have been different must be the same and they must be equal. So that is no different here. We will start with 2 identity elements, E and F. We're not assuming that they're different. And we'll be done with the proof when we have a red line that says, therefore E is equal to F. A good thing to do whenever you start any proof is to unpack your assumptions. We are making the assumption that E is an identity element of our group. If we go back to our group property and write down what that means that E dot A is equal to A dot E, which is just plain old equal to that other group element, A, for every single element in the group. Now, a good thing to do when you have symmetry in a group is to maintain it. So we made this statement about what we knew about E. A very natural next step is to write down what we know about F, not playing favorites with E. Similarly, our group property regarding the identity tells us that F dot B should be equal to B dot F, which should be equal to B for all elements B in our group. Now, here's where we need a little bolt of inspiration as to what to consider. Remember that we're ultimately trying to show that E is equal to F. So we would like to start with some sort of equation that we can manipulate, because that's a great thing to do in math. When we have equations, we often can figure out the next step by trying to do different things to that equation. But we need just the right one here, and it's probably an equation that involves the two variables we're interested in, E and F. Fundamental to the group is the binary operation and the method of combining things. So one thing that might be a good thing to look at that uses the two variables of interest to us and uses the operation of the group is E dot F. Now, just as we did at the beginning of the proof, where we did one thing with respect to E and then did it again with respect to F, I want to do the same thing when we're looking at this element of the group, E dot F. I'd like to know what this element of the group is. So the first thing we're going to do is play favorites, and we're going to remember that E is special. E is an identity element of the group. And F over here, F is going to act as the A in the first sentence. We're going to forget that F is special, and we're just going to think about F as any old element of the group and focus on the fact that E is an identity element of the group. Because E is an identity element of G, forgetting that F is special, E dot F should be equal to F dot E, should be equal to just the element F. Now, I did a thing to this equation, playing favorites with E and thinking about the fact that E was an identity element of the group, and I drew a conclusion. Again, don't play favorites. Go back to the drawing board, look at that E dot F, think of F as special and F as an identity of the group, and forget about the fact that E is special. E can just take on the role of B in this equation right here and be any other element of the group. When we do that, we look at E dot F, thinking of F as special, as an identity of the group, and E as any old element of the group. When we combine any element of the group with the identity, we should get that element back. So on the one hand, E dot F is equal to F. On the other hand, E dot F is equal to E, and here we are at the end of the proof. By transitivity of equality, F is equal to E.